Hello, this is Tom Klupper, and welcome back to part 3 of learning on how to use the electronic desktop software. We're going to start focusing on microstrip lines from here on out. And the first thing we want to do is characterize the substrate we're going to use in our projects. So what we do, or what I did, is I contacted Park, which is the company we're going to use to make up the printed circuit boards, and they told me this is the material they use. KB6167F is the type of FR4 they use. If you look at the fiberglass weave and the epoxy resin, you can see what the cross-section of a printed circuit board looks like. So what we want to know is what are the dielectric properties of that material. So they were kind enough to send me some, and I etched off any of the copper, so I just had the substrate, and then I used what's called a split post dielectric resonator to measure decay and loss tangent at a given frequency. Just shows you a picture of it. It's a resonant cavity that you measure the resonance empty, and then you slide the sample in and you measure it at about 2.9 gigahertz, and from that we were able to estimate that the decay is about 4.8 and the loss tangent is 0.016. So with that data, I went down and said, well, the substrate, which is the dielectric thickness, is 30 mils. The trace, or the copper on both sides, are 2 ounce or 2.8 mils. And we're able to calculate the width of a microstrip line to be 51 mils nominally for 50 ohms. So what I did is I took that information and I designed a test board using the software. And what I typically do is I'll design one trace in the middle, which is nominal, and then I'll put one trace to the left, which is a little low, which is 47 mils, which should be a little high impedance, and then one trace on the right, which is a little wider, 55 mils, which should be lower. And essentially what I'm doing is bracketing the impedance, made up the board, and then tested it using this test fixture. So this test fixture, you can kind of put the bare board in and press down these connectors and test it without having to actually solder a connector on both ends. So if we look at the data, what we have here is the S parameter data, S11, for each one of them converted in what's called time domain, or TDR, time domain reflectometry mode, and it shows the impedance as a function of time of each one of these traces. So you can see that in fact they are pretty good. The middle trace is very close to 50 ohms. The way you find out what the impedance is you kind of go right behind the connector and you take a snapshot. So if you look at this, you can tell that the boards may be a little bit high. So the 50 ohm board maybe 50.5 ohms, a little bit higher than that, but it's pretty close. But so it is a little bit high, which means that my guesstimate for decay of 4.8 may be a little high, but we'll check that out further on. So the way we're going to do this is, again, Park gives you 3 boards. So the first board, the nominal board, is 2.292 inches from end to end. So what I did is I measured board 1, shown here, got its S parameters, and then I cut it down literally with a pair of scissors to something smaller, ended up being 0.874 inches. The actual length of that doesn't matter. It's more importantly that I know the length of the original board and the length of the smaller board. So I measured these 2 boards and I collect the S parameters, and what I'm going to do, I'm going to take S21 for the longer board, which let's call that X, and S21 for the shorter board, let's call Y, and I'm going to compare them to verify decay and loss tangent. And by compare, we're trying to subtract out the values. So mathematically what that looks like is, let's take a look at this. So S21 for each one of these is a vector quantity. It'll have an amplitude and an angle associated with each one. If we just take S21 of the longer divided by S21 of the shorter, you'll get the ratio of the amplitudes and you'll get the difference of the angles. So all we have to do is just divide these two, plot angle, and that'll show you the difference of the angle. So that'll give us the phase difference. If we take 20 log 10, or the insertion loss of that ratio, what it is, it's the difference in attenuation in dBs of the longer one minus the shorter one. So it does achieve the difference in dB. So this is the math that we're going to apply to try to look at our comparison between the two. So let's go ahead and do this in the software. So what I'm going to do, I opened it up, I'm going to right click and let's just say save as, getting started, and I'm going to call this guy starter part 3. So we have a project. Let's go ahead and create a circuit. And in this case, I'm going to say not do the substrate because I'm going to define it in a little bit. So we have our circuit empty schematic, and let's go ahead and view the component libraries. In this case, I'm going to click on symbols because what I want is I'm going to import the actual S parameter data that I measured. So let's click on import and say I want to put an import. Actually, I'm going to double click and say let's pick the long one first, which is that guy. So this is the data, board 1, trace B, which is a 50 ohm one. It's 2.92 inches. Say OK, and I'm going to drop that right there. Hit the space bar. And let's do it again, import, and we're going to do the shorter one. Say OK. I'm going to drop that right below. Hit the space bar. Let's go ahead and zoom in. Now what we have to do is drop some ports. So let's drop 2 ports on this side and then 2 ports here. Let's hit the space bar and let's connect them up. So what we've done is we've made a device under test be the actual S parameter file that I measured on a network analyzer of those boards that we saw before, where S21 is going to be the insertion loss of the longer trace, the 2.292 inch trace or board, and S43 will be the insertion loss of the shorter guy. So let's go ahead and got our ports. Let's add a analysis, add Nexum setup, linear network analysis. Click on here and say edit linear step, and I'm going to use the same steps that I did when I actually tested it, which is 0.05 gigahertz to 20.05 at 0.05 gigahertz steps. Alrighty, so I've set that up. I'm not going to do any group delay at this time. I may change my mind later, but right now we have our setup. Now let's go ahead and run the analysis. Say analyze or press F10. And it should be pretty quick because the data is already there. It's already measured. It's just read it in from the file and load it in as an element and say great. So I'm going to click on results, click on a standard port, and hit rectangular plot. What I'm going to do, let's just look at the raw data. So make sure I don't get this wrong. So S21 is the longer guy. So we'll look at S21 in dB, and then S43. Add that trace, and that's the shorter one. Okay, so we have the insertion loss of the longer one, insertion loss of the shorter one. Again, it goes pretty wonky out here at high frequencies for a couple reasons. One, this board is not designed to do anything at high frequencies. Using an FR4 board, we're only going to be looking at a couple of gigahertz, probably down in this range. I just tested it all the way up here because that's just what I do, and it doesn't take that much energy to get extra frequency data. So I'm going to call this raw insertion loss. Okay, click on results and say standard report, rectangular plot. I'm going to go S parameters S21 angle in degrees, say new report, and then S43. Again, angle in degrees. We're going to add that trace. And what we're plotting here is the phase. So I'm going to call this raw phase of each of the board. So here we have just the raw insertion loss of the 2 traces and then the raw phase. So what we want is we would like to look at the difference between these two and the difference between these two. So just to let you know, when you look at phase, it always starts off at 0 and goes negative, but since it's the arctan function, it stops at -180 and it flips around to +180 and then goes down. So you see one has more of these flips than the other one does, and essentially if a transmission line is shorter, it'll have less of these transitions than if it's longer. So it's almost like an accordion. So when I look at this, I can tell that the red one here is longer because it's almost been accordioned in, and so there's more transitions for a given band than this one. So it's just kind of I can kind of look at that and go, oh yeah, this one's electrically shorter than that one. And that'll come in handy in a second here. So okay, let's go ahead and do the comparison. I'm going to click on results, right click, and create another standard report. Except this time I'm going to go down to output variables, click on that, and I'm going to call this one S21 delta. I spelled that right? Okay. So that's going to be a variable name. And I'm going to say that this one is going to be S21. I double clicked here and it showed up in the expression. This is the vector S21 S parameter. I'm going to hit divided by and go S43 and say add. So now we have a variable called S21 delta, and it's literally equal to S21 divided by S41. It should generate a complex result. So you say done. So now I'm going to take my output variable S21 delta. It's just a complex number. I'm going to plot dB times 20 or 20 log of that. Because remember, it doesn't know it's an S parameter. It's just a variable. So it's going to calculate 20 dB, and we're going to say new report. Okay, and say close. So this is the difference now in insertion loss difference. Okay, and let's just call this one, just plot insertion loss. I did this right. And I'm going to do the same thing. I'm going to create a new report, rectangular plot, variables. Oop, no, let's go back and yeah, it's okay. S21's there. Okay, so output variables, I'm sorry, S21 delta, and angle in degrees this time. And close. So now this is the difference in phase between those two lengths of line. So just to let you know, I'm going to go back to the PDF for a second here. What we're looking at is the difference of insertion loss if I took this trace insertion loss and subtracted that one from it. And the difference in that length would be that minus that. So 2.292 minus 0.874 is 1.418 inches. And that's the same for insertion loss. So if I take the length of this in phase, subtract the length of that, I'll get the length of a 1.418 piece of line where I've essentially removed any of the connector effects. So I'm just looking at a length of transmission line. So let's go ahead and do that. So let's go back to our circuit, and I'm going to add a microstrip line. Now I'm going to define data. So click on data, right click, and say add substrate definition, and you'll get this window as soon as it comes up here. Let's call this FR4. I'm going to change this to mils. Find it. Where are you? There you are. So the height of the substrate, H, is 30 mils. So that's right here. That's the distance of just the dielectric. We're saying the DK is 4.8 measured from our split post cavity. Tan delta is 0.016. We'll say height is 25 millimeters. That's about an inch. We'll just say that's there. And then the thickness of the copper is 2.8 mils, which is 2 ounce. And I'll just leave roughness 0 for right now. Okay, so we have a basic definition of a substrate. Say OK. Now, one thing you can do is see where it says circuit. You can right click and go down here to TRL. And these are a set of calculators that you can do coax, etc., strip line, microstrip. I can say single. And I can calculate based off of the FR4 definition. You say OK. It'll come with this little calculator. So what we can do is say, all right, I want 50 ohms, say frequency 1. Notice it filled in all the parameters from the substrate. So if I just say synthesize, let's go back to mils, synthesize. See how it says, oh, it should be 51 mils. That's the width of this line for a 50 ohm microstrip trace. This is essentially how I came up with that 51 mil number that I mentioned before, just using this calculator. Now again, you can go in here and change any of these, but for right now, this just gives you an idea of how to use the calculator. Okay, so let's go back to say components, and I'm going to select not ideal. So we're not using the ideal, we're going to use the actual distributed physical components, and we're going to select the microstrip one, transmission lines, and you can do a lot of microstrip components, and we're going to use a number of these later on. We're going to click on transmission line physical length, double click on it, come over here and drop that here, hit the space bar. Let's go ahead and put two new ports. So this one's going to be port 5, 6, space bar, and let's connect this up. So now 5, 6 will be a 2-port of our transmission line. I'm going to double click on this. Remember we said the width is 51 mil, and the length is going to be our 1.418 inches. That's the, I'd mentioned that's the difference between these two lines. Notice that it shows the TRL button here, so you can actually click this and you'll get that same calculator. It's kind of built right into there. Yeah, all right, and we've already done that. We've already calculated 51, etc. And if you just click on components, just to let you know, come down here to substrate, you can see this is where it's picked up the FR4 substrate. If you had multiple substrates defined, you could select which substrate you're going to use for this element. Okay, so now we have a simple microstrip line, and let's go ahead and reanalyze our circuit. And we're going to go here. So essentially, this model should be the same as the difference between these two. So when we go over to insertion loss, this shows the insertion loss of the difference. So let's go ahead and add an S parameter, and it's going to be 6.5 dBs, and say add trace, close. So there's the model, there's the actual data, and there's the model. Let me do one thing first, which is you can see how it kind of goes off the rails, a higher frequency. So I'm going to cut this down because there's no reason for us to be looking at the whole band. So we're going to go from 0 to, let's just say, 4 gigahertz, and we're going to go to 0.5 gigahertz steps, apply, and we're only going to go to a half a dB. So let's go to the Y scaling, and the min's going to be minus 0.5, max is 0, and we're going to go 0.1 dB steps. Okay. All right. Now we've kind of blown this up a little bit. We can see that our model is showing the data a little low. Right? So here's our actual data, and then there's the model. So let's go back to our substrate definition and go, all right, well, let's just, for grins. Now, what's interesting is you can't change this directly. So we're just going to leave it as copper. But let's just say that we think that the tan delta at 0.06 is a little low. So 0.19, let's try that. So it's very possible. If you notice from the cross section of the circuit board, I'm just going to say, okay, let me just show you that real quick. Let's go back to here. Up, come on. There we go. Okay. See how this has got a lot of fiberglass and resin? It's very possible that the way this measures it, which is the electric field in the plane of the substrate, is not going to give you exactly the loss tangent equivalent that would be for a microstrip where the electric field is in this direction. So just something to keep in mind, a small subtle detail. Okay, so we've changed this to 0.019, and let's go back and calculate, reanalyze. And again, this is the trial and error process of fine-tuning your substrate definition in. Okay, got a lot closer. We could even probably tweak that in a little bit more. And one way I'm going to do that, I happen to know that a typical roughness for copper is about 4 micron. And we can go into surface roughness of copper, but that's a typical roughness for FR4 or any circuit board. So I'm just going to say it's a 4 micron roughness. Hit the analyze, and let's take a look at our model again. Oh, there we go. That's a pretty good match there, I'd say. So I would say we have the attenuation characteristics fine-tuned in. Let's go down here to our phase, and we're going to add our S parameter value of our model, and we're going to that's a 6.5, and then we're going to look at angle. We're going to add that trace, say close. And let's go ahead and do the same thing here. I'm going to double click X and go 0.5 gigahertz to 4 gigahertz. We can leave it at 0, it doesn't really matter. But we're going to go 0.5 gigahertz steps. We're just kind of blowing this up a little bit there so we can see. Alrighty, so here's our red trace is the actual data, and the green trace is the model data. So look at this. So the red trace is a little bit further out, which means it looks like it's a little shorter electrically, where the green trace is a little bit to the left. It's starting to kind of accordion in just slightly. So that means it's a little bit long electrically, which means that the decay is probably a little high. So let's go back to our FR4, and we said, well, it could be let's try 4.7. And I'm going to hit F10 to analyze. And again, this is just kind of a trial and error process that we can use to kind of fine tune things in. I'd say that nails it right away. So I would say based off of this, we have our phase of our actual data, the difference between the two coupons, and our model. And then we have the insertion loss, the actual data, and our model. I would say that we have fine-tuned in the characteristics of our microstrip such that we can use this data to now calculate new microstrip lines in the future. That's it for now, and we will catch you on the next one. Thanks.